I just finished running the calculations this morning, and you are the very first to hear this news. We finally have concrete dates on March 16th, 2026. The Interstellar Object 3I Atlas will make its closest approach to Jupiter, but it isn't just flying by randomly, it is arriving exactly at Jupiter's hemisphere, which is that invisible boundary where the planet's gravity perfectly balances out the pull of the sun. And here is the part that has the astronomy community absolutely frozen. This object is arriving with a precision error of only 1 part in 26,000. To give you a real-world idea of what that means, it is like standing in Los Angeles and throwing a needle all the way to New York City and having it land precisely on the edge of a coin after traveling billions of miles through empty interstellar space, surviving the scorching heat of the sun, and navigating through gravitational turbulence. Atlas is sliding into a specific zone 33.24 million miles from Jupiter with an accuracy margin of just 35,000 meters. No natural comet in history has ever shown this kind of controlled approach. We aren't just guessing about this either. Over 230 observatories around the world tracked a specific course correction. It happened right after perihelion, the moment it was closest to the sun. It happened exactly when it needed to, and exactly where it needed to guide the object straight toward this boundary. If you have been following the 3I Atlas saga and something about this feels impossibly precise to you, hit subscribe right now and drop a like, because we need to break down the math, the maneuver, and the 3 scenarios scientists are watching for next. And what happens next could completely rewrite everything we think we know about visitors from deep space. When 3I Atlas first appeared, moving in from the unknown, it followed a normal hyperbolic trajectory. Its speed, direction, and orbital shape all matched our expectations. A visitor not born in our solar system. Researchers just cataloged it as another rare traveler passing through. Then it got closer to the sun, and the behavior changed. After perihelion, the object displayed what scientists call non-gravitational acceleration. Now, that isn't unusual by itself. Comets experience this when solar heating turns surface ice into vapor, creating jets of gas that act like tiny thrusters. But normally, these jets fire chaotically. Comets twist, spin, and wobble, so their outgassing creates uneven motion that usually cancels itself out, making the path noisy and unpredictable. Atlas behaved differently. The acceleration was weak, but it was highly directional. It pushed the object slightly away from its original track, and the direction of that push was practically perfect for guiding it toward Jupiter's hemisphere boundary. And I don't mean it was close, I mean it was dead on. Over 200 observatories refined their data and reached the same conclusion, and the object was no longer following the path predicted by gravity alone. Every updated model showed a growing match between its new route and the edge of the hemisphere. This level of agreement across global datasets makes the course change very difficult to dismiss. The acceleration pushed Atlas by exactly the amount needed to reach its current target. If that push had been stronger or weaker by even a tiny margin, the object would miss the boundary by millions of miles. And the timing matters just as much. The correction happened sharply after passing the sun, which is the optimal moment for a trajectory adjustment. If it had happened earlier or later, Atlas wouldn't be arriving at this narrow zone whirlpool. The effect could still be natural. The combination of timing, angle, and precision has the scientific community asking what exactly is happening. To understand how extreme this precision is, you have to look at how interstellar objects normally behave. And they enter the solar system with unpredictable rotations and uneven surfaces that react differently to sunlight. Small changes in heating push them in many directions. So astronomers usually expect a wide range of possible outcomes with error margins in the millions of miles. Atlas has broken that expectation. Every new observation shows a slimmer margin of error instead of a wider one. The growing accuracy suggests the object is following a clean, stable line that doesn't match the noisy patterns of natural comet motion. This wasn't a gradual drift. It began sharply after the sun passage. The slight acceleration created exactly the correction needed to slide into the narrow zone around Jupiter. The chance of a natural push happening at the exact strength and direction required is extremely low. This is why researchers are questioning whether simple physics alone can describe this motion. And the effect resembles a final steering adjustment used in spacecraft navigation rather than a random burst of gas. Think of it this comparison. Imagine throwing a dart while blindfolded from one continent and hitting a bullseye on another. Now imagine the dart self-corrects mid-flight to compensate for wind, gravity, and drag, all without guidance systems. That is the level of precision Atlas is demonstrating. Natural processes simply don't produce this kind of accuracy across interstellar distances. And the Hill sphere marks the region where a planet's gravity becomes stronger than the sun's pull. For Jupiter, this zone stretches tens of millions of miles. And most natural objects never hit this boundary because their paths are shaped by chaotic forces like radiation pressure and collisions. They either fall deeper into Jupiter's well or stay far outside. The boundary acts more like a mathematical line than a physical target, since no object normally aims for this thin transition zone. The fact that Atlas is approaching it so precisely is startling, but the boundary is also unique because forces inside it behave differently from forces outside. So when an object enters the Hill sphere, Jupiter's gravity begins to dominate. The object can be captured, accelerated, or ejected. Outside, the sun leads the edge between these two regions, is a fragile border where a small shift in direction or speed creates completely different futures. It is extremely rare for any comet to match the exact distance where gravitational powers balance each other. Space agencies understand this intimately. When engineers design spacecraft routes, they rely on Jupiter's deep gravitational well to perform slingshot maneuvers. And these require careful planning and precise timing because even slight misalignment pushes a spacecraft into a totally different orbit, missing the edge of the Hill sphere by only a few thousand. Miles can shift a mission by millions of miles later in the journey. It is challenging even for human technology to reach this boundary with exact accuracy. Seeing an interstellar object behave with similar precision raises critical questions about the forces acting on it. The shift near the sun appears to match what a controlled adjustment would look like during a space mission. The object received a gentle push that moved it away from its earlier path. And the amount of that push was almost exactly what was required to guide it toward Jupiter's Hill sphere edge. Scientists have proposed four main explanations, and none fully resolve the observations. First is observational error. Early measurements can contain mistakes, but 230 observatories have tracked Atlas, and every new dataset confirms the same path. The error explanation becomes harder to support and the object keeps matching predictions with unusual precision. Second is natural outgassing. Heating can trigger repeated gas jets that move a comet gently in one direction. If jets line up with cracks or weak spots on the surface, and they can create forces that look organized. And the problem is that the jets would need to fire at exactly the right strength and angle for a long period. Even small changes would send Atlas far from its current target. The chain of coincidences required makes this scenario possible, but very unlikely. Third is simple coincidence. The solar system has existed for billions of years, and many interstellar objects may have visited undetected. If even a few passed near Jupiter's Hill sphere by chance, Atlas could be another rare but natural example. It's not impossible, but the rarity of the alignment and the clean path leading to this moment make coincidence weak. Answer fourth is controlled or semi-controlled motion. This doesn't require artificial origin. A unique structure or chemical makeup could allow the object to use sunlight, gravity, or internal processes to guide itself without technology. Some researchers propose that if advanced civilizations navigate through planetary systems, they might use gravity wells and boundary zones like Jupiter's Hill sphere. While there's no direct evidence, Atlas's behavior keeps this question open. If the answer is an error, coincidence, or normal outgassing, what kind of process produces such steady, precise motion? Three scenarios dominate the scientific discussion. First is fragmentation. The competing pull between Jupiter and the Sun creates strong tidal stress. Many comets crack when exposed to rapid gravity changes. If Atlas breaks apart, fragmentation could reveal internal structure. No telescope has seen layers, cavities, or unusual materials, yet this would provide direct evidence of how it formed in another star system. Second is payload release. And some researchers believe Atlas could release smaller bodies or particles as it slows near the boundary. Natural objects sometimes shed fragments, but doing so near a gravitational transition zone could suggest organized processes. If Atlas drops pieces that follow stable orbits or drift in recognizable patterns, astronomers would study whether they behave like normal comet debris. Any pattern looking too neat or coordinated would challenge our understanding of what interstellar objects can do. Third is a directional change. Atlas may shift trajectory once it reaches Jupiter's domain edge. A motion change could show the object is sensitive to the gravitational landscape and capable of reacting in ways that don't fit simple comet models. And if it turns toward a new path, slows further, or enters a temporary Jupiter orbit, scientists would gain evidence that its motion involves more than random forces. Even a slight adjustment could become one of the investigation's most important clues. Whether the answer lies in exotic internal processes, unknown natural mechanisms, or something we haven't considered, And the object is forcing a fundamental question: what kind of forces can maintain such consistent, well-aligned motion across billions of miles? March 16th will tell us more. Until then, the precision remains unexplained. The trajectory remains impossibly clean, and the mystery remains wide open. What do you think is guiding 3I Atlas? Is it natural physics we don't understand, or something else? Drop your theory below. Subscribe for the Jupiter Encounter update. And share this with someone who's been watching this object closely, because what happens next could change everything.